Hi there.
So hello everyone, my name is Cedric, this
Daniele.
is Daniele, and I'm Hai, and we work at Square. And today we're going to talk about encrypted data at rest and Hadoop, and specifically how Square is thinking about big data security and a little bit what our ideas are, how we are making our big data infrastructure secure.
You can be in the center, yes.
Logistics problems, as we
And before we start, I would like to say this is still a work in progress, so we have a lot of ideas on how we want to make this possible and what we think are the best solutions to these things. And but we still want to talk about it, talk about the brainstorming we have done and the ideas we have had, and see how other people are solving this problem, and then maybe connect and collaborate on this. And with that, I will give it to Abhay first.
Hey, everyone. So my name is Raj Kumar. I run data engineering at Square. I don't have a formal security background at all, but I am definitely a user. So I'm going to first talk about what we have today, what we want, and sort of I'm going to hand it off to these guys to actually talk about how we're going to try to implement this. So a little bit of background. So our current setup, we use Hadoop for data storage and analysis. We are storing all of our records in files, as you normally would in HDFS. And each record is encoded as a protocol buffer. We've decided across the board that we would encode everything as protos. And this is sort of a one decision we made for all of our RPCs. And so what we just did was transition this over to a data infrastructure. The one thing that we haven't done yet is put any sensitive data in Hadoop. And this has primarily been the case because we didn't quite have a story around this yet, and hopefully this talk will give you an idea of what the story is going to be. So we use Hadoop for analytics and data products. We do a lot of analytics internally just to understand our customers. We try to offer our buyers and our merchants data products as well, and we're using Hadoop as one of our tools here. And redacted data is surprisingly useful. Around 80% of the things that we need, we can just do with redacted data. But sometimes it's not enough. So here's some problems. So one of the problems that we have today is that access control is restricted at the file level. Even if we Kerberize a cluster, we'll still be limited by files. And what if we have some sensitive data mixed in with the unsensitive stuff? And we can do there are a lot of solutions here that we proposed. But really the important thing is, how do you know which data is sensitive? If you just have protocol buffers encoded on disk, it'd be really great if you tag that sensitive data. So here are a couple of solutions we went through, and some of these are my solutions, and then I immediately just said, no, we're not going to do that. One thing was have a separate Hadoop cluster. And this certainly can work, but the common thing happens, you'll have a lot of overhead, obviously. Like, you're going to have multiple clusters, and really it won't be necessarily clear how to separate our data. And actually, one of the biggest problems that I've had with this is that everyone's going to have access to the secure one and not the insecure one, so you're going to have to scale that up. And now this insecure one becomes just completely empty, and no one's actually going to use it. The other option is to give broad access and just audit logs. Certainly a great option, but one of the things that we were trying to do is try something a little different. Let's see if we can throw a little bit of engineering at this problem and see if we can do something slightly different, and hopefully we succeed. And we like crypto, so maybe we can try something on the crypto front. So I'm going to hand it off to Daniele to talk about securing the data.
Hi there. Can you hear me? So yeah, the set of broad requirements we had for this problem is, at the beginning, was pretty fuzzy because there was like an interface problem at the beginning, because the security people had to go to the data people and say, so what is this thing? And how do we interface with each other? And how do we understand all the data pipeline and everywhere where things could go wrong? So as Abhay said, there is this first problem accessing individual records inside protobufs, and how do you even tag the data inside protobufs? So this is one of the requirements we wanted to solve. So accessing individual records and tagging the data inside it. We also didn't want to just support HDFS and Hadoop, because, for example, the data that gets into Hadoop comes from like a Kafka message bus. And now, if you know about Kafka, you also know that the security story there is not very good. Everybody can consume any topic. So we wanted to have a solution that scaled also to all these types of stores. And this is a very key point. This is a very important point. We wanted to be transparent to programmers and developers and software engineers. And this is where most of the crypto breaks, because people give interfaces to crypto APIs as if it was any other API. But crypto APIs are much trickier than that. So the devil is in the detail, and there is a lot of unsafe options and maybe a really small subset of safe options. So we wanted to give the least amount of control to the developers and make it just work by magic. And of course, you want to have all the nice things about crypto that, you don't want to make the mistakes of not having crypto agility or supporting key rotation, because otherwise down the line, in a couple of years, you will regret that very badly. And when we talk about encryption of data, we wanted to make sure that the data doesn't live with the keys. That that is meaningless. That security, for the most part, tends to be security theater. We wanted to, as I said, we wanted to support field-level encryption. We needed to patch the libraries, the serialized and deserialized protobufs, so that we could make encryption and decryption automatic and transparent. And on the encryption side, we wanted to, at a broad level, we wanted to support public key cryptography, so that there is an entity that owns the private keys and distributes the public keys to data producers, so that data producers can encrypt data offline, so without having to contact the service. And on the decryption side, since, as I said, we wanted to have this requirement on not storing keys with data, there has to be some sort of like online access to this decryption and encryption service in order to get the data out. And with that, I'll give control to Cedric.
All right. So let's say we want to actually encrypt everything and then decrypt it in a secure fashion. And we started brainstorming on what would be the best solution to this and how could we solve it in, just from a security point of view, the best, most secure solution. I thought, let's reuse our existing online encryption and decryption service. So at Square, we already have services that do online encryption and decryption. So let's just use that. It's easy. We're just going to adapt it to our needs, and we're just going to scale it up. So the encryption and decryption service that we have at Square is called Bletchley. And our colleagues Nathan Macaulay and Diogo Monica are later going to talk about this in a little bit more detail. But it's pretty simple. First of all, let's assume that authorization is a solved problem, because for us it is. So when service A or service B talk to each other, when service A talk to Bletchley, everybody always authenticates. So every connection is authenticated via mutual TLS. Everyone has a certificate that's already taken care of. On the left-hand side, we have our service, Bletchley, which is a hardware security module which stores keys. Let's say we have some data producer, service A, which wants to get a message from somewhere, wants to encrypt it, store it safely, whatever. It can talk to Bletchley and say, please give me a public key, and let B decrypt whatever I encrypt to this public key. Bletchley will generate a new key pair. It will keep the private key in the hardware security module. It will hand out the public key to service A, and service A can then use that offline to encrypt whatever data it wants. At some point later, those messages will be sent to service B. Service B can take the ciphertext and can then just hand it off to Bletchley. Bletchley will know that, this ciphertext has been encrypted for service B, and this is service B that is connecting to me. So I can decrypt it, and I can give back the plain text. And this gives us a lot of advantages. So first of all keys are stored in hardware security modules. Well, the private keys are stored in hardware security modules, so they can't just be stolen or exfiltrated. The decryption must always happen online. So if I have a ciphertext, if I want to decrypt it and get back the plain text, I always have to go talk to this service. So we can monitor that. We can rate limit. We can, make sure nobody is doing anything funny. The service can perform access control. So I can say, which service is allowed to decrypt from which key. Everything's is checked appropriately. We never store the data together with the keys. So Bletchley is an extremely simple service. It just hands out public keys. It takes ciphertexts, decrypts them, and returns the plaintext. And the data and the keys are always completely separate. And we're reusing existing infrastructure, so that makes it obviously easy for us. So essentially, what this means is that access to the data reduces to access to the credentials to access Bletchley. So we can control who has access to the data by controlling who can access Bletchley. However, in the context of using this for a big data installation and potentially also using this for in the context of a MapReduce job, there are a few problems with this model. So first of all, as it's currently implemented, it assumes that we know the consumer in advance. So once we retrieve a public key, we have to say, who do we want to encrypt to? But data could be used in different contexts. We could have a lot of different services producing a lot of different data that we want to analyze all together. We don't know that yet. Not all data is created equal. So we may have data that is more or less sensitive. Maybe a customer ID is not so sensitive, but maybe an email address or a name is more sensitive, and we somehow want to distinguish between those different levels. But the biggest issue with this is scalability. Because if you want to run a MapReduce job across 1,000 worker nodes, and you have 1,000 nodes doing 1,000 parallel requests to your decryption service, it becomes very difficult to scale that up. And so the way we thought about the decryption overhead at first is to say, well, decryption of a round trip time takes approximately 15 milliseconds. And that's just based on our experience, because we have been running this service for a while. And we thought it's approximately the same order of magnitude as a disk seek. So disk seek is obviously a bit faster, but it's still milliseconds. But Hadoop actually optimizes disk seeks away. So when you do run a MapReduce job, Hadoop tries to avoid disk seeks as much as possible, because that causes a lot of slowdown. And by forcing decryption in this way, we are essentially, it's like we were to force you to join on a table, so that you then constantly have to get data from, plus that table is then going to be far away on a different host. So that just makes it too slow, and we're not really getting anywhere with this solution in terms of scalability. So we thought about a different solution for fixing this. Since the call to the decryption service is what introduces the overhead, is we just reduce the number of calls by implementing batched operations. So instead of encrypting each individual piece of data via the decryption service, we just encrypt a bunch of fields with a random AES key. And we just reuse that key for a while. So we have a service that's producing data, and it generates its random key. It reuses that for, let's say, 10,000 records. Then it generates a new key and reuses that again. This way, we don't have to call the encryption service on every single decryption, because we have like a batch that is encrypted with the same key. And we can just embed the encrypted AES key with the data, so that whenever we look at a record, we can take the embedded AES key. We can decrypt that via the online service, but then we cache it and we reuse it, and it'll be valid for that batch that it was used for. So, however, this assumes that we have good data access locality, because if we let services just produce these batches that are encrypted with the same key, that's great. If we then look at a bunch of data that was produced all in the same batch, then we only have to do one decryption to get access to that whole batch. That's fantastic, instead of doing, let's say, 10,000 online decryptions. But we have parallelism. We have a bunch of worker nodes that are working on this at the same time. We have lots of different services that produce this data. So we can't actually guarantee that we'll get the nice case out of this. So the data may be distributed in a worst case fashion, where every worker node has exactly one record from each batch, each encrypted with a different key, and then we're back to the same problem that we had before. And the overhead still grows as the data grows. So if, let's say, tomorrow we would start generating 10 times as much data as we are generating today, then our overhead would also significantly increase. So we talked to our data engineering team about these different solutions. And we brainstormed about how do we actually analyze the data. Because we were thinking about doing these batch decryptions. But generally, when you analyze data, you're not going to say, oh, I want to look at the last 10,000 records that have been produced by service A. That just doesn't really happen. Instead, what analysts do is that they analyze based on chunks of time. So you'll say, I want to look at everything that happened in the last 3 months. I want to look at everything that happened in the last week, for instance. So what we're just going to do is we are going to change encryption keys based on a certain time interval. So for instance, we could change the encryption keys every day. And during that day, we just use the same key to encrypt all of the data. Our worker nodes in our cluster, they simply retrieve the keys that they need when the job starts up. So if I know I'm going to analyze everything from the last 30 days, then I just get the keys that I need for that data or for that time span. And that gives us a fixed overhead. So we know in advance what the overhead is going to be versus the previous solution where it was a little bit unclear and it depended very highly on how the data was distributed across nodes, which is very unpredictable. And the number of records is not a factor anymore. So if we produce 1 million, 10 million, 1 billion records each day, the overhead stays the same and doesn't scale linearly with the number of records. Now, Daniele is going to talk a bit about the security implications.
So when proposing a solution like this, it's always hard to think about why are we doing this and does it even make sense? Because we went from like a completely online decryption service to a decryption service that now batches by day, right? And some of the online guarantees are lost, some of them are kept. And you always have to kind of take a step back and understand whether or not what you're doing even makes sense from a security point of view, or are you convincing yourself that you're introducing security when you're just introducing overhead and making everybody's life more difficult. So the way that you think about the security implications of the change, I think, is that it does still provide like broad security guarantees, and there are things it does and things it doesn't do anymore. So what it does do still is that if somebody just walks into your data center somehow, takes a box away, they're not going to be able to get the data because the data is behind like several layers of firewalls and networks and access controls. So there's going to be some physical separation between their data that they just got and the ability to decrypt in it. So that's a good thing. Then you're also protected against any sort of attack that sort of similarly to an SQL injection allows you to retrieve the data without being able to actually run like a Turing complete piece of code on that box. And then you basically still have to understand that as long as you can keep separation of who can access what credentials to access Bletchley, you have a very clean separation of who can get what data. So overall, we thought that this was a very good security trade-off. But in order to share, I think a cautionary tale when implementing those things is always trying to take a step back and understanding whether or not you're doing real security or not.
Yeah. So some other stuff that's also necessary for this to actually work is you need to Kerberize Hadoop. And what we mean by that is that when analysts use the cluster, they log in with their credentials. And the Hadoop cluster Kerberizes and then accesses the keys based on who is logged in. So this way we can grant access to certain data to individual analysts.
The credentials to access Bletchley.
Yeah.
Right. Otherwise, your Hadoop jobs run as whatever user you just pass in, and you can make that up. Yeah.
We still want to use different keys for different data. So we still want to distinguish between data that's more or less sensitive than, we want to have sort of different levels that we can grant access to. We've chosen to have 2 levels. The first is personal data, such as maybe an email address. And the second level that we have is anything that's more sensitive than that. And what we also have, or what we want to have, is the ability to run re-encryption jobs. So if this model, this works really nicely. If we detect that one of the crypto algorithms that we used was, gets broken, we could just run a Hadoop job to retrieve the data, re-encrypt it with a new key, and then write it back. So let's talk about a little bit more in detail about the implementation of this, and specifically how it works in conjunction with protocol buffers. Do you want to take this one?
I mean, so as I said, we wanted to keep this idea that developers should just be able to use encryption without having to necessarily understand what cipher suits, what HMACing, if they have to do MAC and then encrypt or encrypt and MAC. Those are things that they shouldn't be worried about. And the nice thing about protocol buffers, I mean, most of you, probably every one of you is familiar with them, but just as a small primer, they're a way of specifying a data format that, like this. So yeah, you have a customer that has like 3 fields. And the nice thing about protocol buffers is actually they compile into the code that you're actually going to use them in, and they give you like a generic interface to how you access the data. So they give you getters and setters and builders and things that you can use to serialize and deserialize. And what happens is that basically there is a compiler that takes the data definition and spits out this piece of code here that basically allows you to actually use that data in your language. And the great thing about this from a security point of view, there are pros and cons of using protocol buffers, but the great thing about this from a security point of view is that we can hook into this thing. By modifying the protocol, the protobuf compiler, we can actually put interceptors here that implement whatever crypto we need. And now it's only a problem of tagging the data such that the interceptors know what data they have to encrypt or sign or whatever. So that's a great thing about protocol buffers for us.
Yeah, so we want to do essentially what Daniele said. So we already actually have a custom patched protocol buffer compiler internally, which is why we thought this is going to be pretty easy. We already have it run on every machine. We have people who work on it. We have people who have expertise with it. So all we need to do is expose hooks into the serializer and deserializer, and then we can hook into that, and we can encrypt and decrypt whatever we want. And we just install the hooks automatically in our service framework, so developers don't have to care about it. And so this is what we came up with first. This is what we wanted it to look like, and this is actually what it does look like. So this is the same definitions as before. So it's the regular protocol buffer data definition language, but we now have extensions that are attached to this. So if you look at the customer record, you'll see that, for instance, the second field, which is the name, has now been tagged with squareup.encrypted equals personal. And what we mean by this is that this field is going to be encrypted, and the security level is that this is personal data. And that's everything you have to do as a developer, is when you write your service, when you have your data definitions that you write like this, you can just annotate everything you want. Hey, I want this to be encrypted. You do it. And then when you serialize it, it'll be encrypted transparently. You don't have to do anything else. If you deserialize it, it will be decrypted if you have the permissions automatically. If you don't have the permissions, you'll just get a garbled string that is encrypted. And that'll work immediately. You don't have to care. Another thing that we wanted to do while we were at it anyway was to say, hey, let's also add the functionality for signing fields. Since we like crypto and signing is a great crypto thing. So we also added the squareup.signed extension, where you can just annotate fields that you want to be signed, and then the signature will automatically be attached at the end of the protocol buffer, including those fields. So we did this using interceptors, and the interceptors that we have just encrypt and sign based on the fields extensions that you've seen. So if you want an encrypted field, you annotate it, done. If you want a signed field, you annotate it, it's also done. And we can have additional goodies as well. So we also have an extension called squareup.redacted, which will automatically remove fields if you serialize a protocol buffer to a string. this is really great for logging. So if you have sensitive data in a protocol buffer, you can just say, hey, this is redacted. And then if it ends up in a log, our proto library will automatically remove those fields. So you won't even see them.
Really useful for card numbers.
Yeah. And there's lots of potential overuses that we could have for these interceptors. We could have interceptors that automatically scan for sensitive data that's end up in the wrong place, or that implements any other transformation on a message. And I think this is a very powerful idea.
And yeah, just to interject a second, we are currently working in our own fork, internal fork of the proto compiler in a proto runtime. But I think this is one of the things in which we will be happy to share it back, so that we contribute back to the community. The community doesn't diverge from us. We don't diverge from the community. So if any of you has interest in these things, please let us know. We'd be happy to talk to you more in detail about it.
So a bunch of initial roadblocks that we had with this is that it actually turned out to be trickier than we thought. And there was a lot of discussions around the design of this. Essentially, we have a lot of requirements, right? We have the perfect middleware design problem with this, because we care about serialization of data and we care about deserialization of data. We care about making sure there's a nice round trip, that it works as expected. We want to hook into an already existing library and intercept what is happening. And we want to make sure that this is still backwards compatible. We want to make sure that this works with our own code and that it works with third-party libraries that we use. We want to make sure that it works transparently when our developers use it. But we also want to have the ability to ourselves use it explicitly if we have to implement certain specific operations. The concerns of threat safety, we want to have all interceptors registered on startup of our service framework. But what if you have a separate thread that, for some reason you want to use different interceptors, you want to implement special operations, whatever. It's a possibility. And it's just also, how do we design a good API around this? How do we design a good API for implementing interceptors? How do we make sure the API from outside is nice when you want to use it, and so on. So just a quick overview over what an interceptor does is you just look at all fields. Does it have an extension that we're interested in? If so, we apply the interceptor for the given extension. And that's it. But we also do a lot of internal optimizations. So we don't want to iterate over every field of every proto we ever serialize. We don't want to look at every interceptor that's ever registered for every extension. So we do a lot of internal caching so that when we serialize the same proto definition twice, or deserialize the same proto definition twice, we already have all of that stuff available and cached, and we don't have to look it up anymore. For encryptions, our interceptor just replaces the fields with their ciphertext. So if you have a string or a byte array, we just remove that and we put the ciphertext there. This is nice and backwards compatible. If you don't have an interceptor for decrypting, you'll just see the garbled encrypted string. And we attach some metadata about which key we use to the message. For signing, you essentially select which values you want to be signed by having the annotation. And we just attach one global signature at the end of the protobuf. There are a bunch of limitations with this. So for encryption, we only support variable length types. So you can't encrypt an integer that's part of a protocol buffer, because what we do is replace it with the ciphertext. And if you only have a 32-bit integer, it becomes kind of difficult to replace it with the ciphertext without breaking the format. So it's just strings and byte arrays. We also don't support transforming nested messages. So one thing that protocol buffers supports is that you can have nested sub-messages. And we don't allow you to currently encrypt or sign these, mainly because it's not really functionality we need, and also because it becomes very difficult very quickly. What if you have an interceptor that has a transformation on the sub-message, and an interceptor that has transformation on the top-level message? Which order do you apply them in? How do you do about breaking backwards compatibility with other implementations? And so we just decided we're not going to look at this.
And you can't just replace a message, the bytes of a message with a bytes of an encrypted message. It's just the proto parser will break.
Yeah, so a protocol buffer parser from another library that doesn't have this implemented would then totally break because it's going to see just garbage data from its point of view. We have a bunch of other ideas for this. So we thought maybe we could also allow fields to be signed by different services. We could use this for a lot of different purposes. For instance, you could distribute signed protos for name resolution, which is something we're also looking into. You could distribute signed configuration updates like this. And we have high hopes for essentially using this across our infrastructure for various crypto needs.
Yeah, and that's over our internal Zookeeper installation. So again, it's supporting different data stores and different use scenarios.
Yeah. There are some drawbacks to this. First of all, support internally is limited to Java right now. We don't exclusively code Java. And in order to support it, you'll have to have a patch protocompiler for each language. And as we talked about, patching protocompilers is more difficult than we thought. So there is some overhead involved. You have to be careful with changes to semantics to protocol buffers. So protocol buffers are also, you could assume to be backwards and forwards compatible. But depending on which changes you implement, which transformations you implement as interceptors, you could break that. If you have a field that was encrypted and you remove that encrypted annotation, you're not going to be able to read old data anymore. So you got to be careful. And developers still need to be thought about using these extensions. So for instance, the redacted extension is something we had for longer than that. But we still have to actively go to developers and tell them, please use this. It's a lot easier than teaching them whether to use Mac and Encrypt or Mac and Encrypt. Some open questions that we still have is, how do we carry such access controls to Hive? Actually, we talked to our data engineering team, and they have some very good ideas on this, but we haven't implemented them yet.
Yep. Generally, the idea that we've had is that we can implement this in custom serializers and deserializers for Hive, and we should be able to figure it out as part of a Hive UDF function.
The second thing is, how do we get better integration with Hadoop? So we want this to be transparent and not have to just diverge from the rest of the ecosystem too much.
There are a couple of other projects out there, like the Apache Sentry project that Cloudera is backing, and Intel's working on the Rhino project. So we want to make sure that we're compatible with some of these things and actually use some of the benefits that they might be coming out with.
Yep. And finally, how have others solved the same problem is, or what do you think of our solution? And that's it.
Do we have time for questions? Or?
Yeah. Anyone have questions for these guys?
I was just wondering if this architecture had any particular implications for PCI compliance. I thought of it when you said you wanted to share the data in the same cluster.
So yeah, we don't currently have any plans to storing PCI sensitive data in that cluster. We have online tokenization, online encryption services for that sort of things. They live in different firewall zones. We try to shield the rest of the company as much as we can from that level of burden. So, and we apply, least privilege to everything, so including card data.
What we are doing with card data, the things that we can store, like card numbers, we are tokenizing them, and those tokens do end up in Hadoop. So an analyst could, match two cards that are the same card number, for example, if they need to.
Have you had any developer pushback from changing how their how the protocol buffers work? Something that would normally be a fast file-based offline operation now is how talks over the network.
I mean, the data engineering team completely freaked out when we when we told them that we wanted to do this.
Not bad.
I think with the batching, you can potentially get a good trade-off. And we I think everybody understands that at Square we want to limit data access to only the people that really need it. And we went back and forth with multiple ideas, and eventually we agreed that some level of encryption was needed to put access control on top of Hadoop. We couldn't find anything else. So it is a cost, but something we're willing to take.
Yeah, and the nice thing about it is that the cost is front end, right? It's at the beginning of the job. You, if with good indices and good metadata about the data you're storing in Hadoop, you can sort of sample and understand what keys you need in the beginning and run that online part just in the beginning and pass that along. Yeah, so that kind of, it's just one step, which makes a big difference. So you're not actually running RPC during the job itself.
Hey, Rusty Sears from Microsoft. I'm wondering how hard it would be to, if a malicious insider, had access to the encrypted fields, how hard it would be for them to write a job that downloads all your keys and it just sends them to their laptop. And if you've thought about
if you think about it, every time you can commit code that runs on the boxes that have access to the data, you can always do malicious things, right? So let's say that I could deploy one of our payment services that now, instead of only processing cards, also took those cards, stored them somewhere, and then FTP them somewhere else. So if you think about this attack, there is really nothing you can do apart from making sure that people don't commit malicious code.
So I was wondering more about ad hoc MapReduce jobs as opposed to committing production code, where of course you can't protect against attacks.
Yeah, the way I think about ad hoc MapReduce jobs is that, again, I want to apply the principle of least privilege, giving as few analysts as possible, maybe for time-bounded periods. If they have to do a specific data analysis, they'll ask us with some quick request saying, hey, I need to analyze a customer's name. Can you please provide me access for a week so that I can do this thing? And then I'm going to get the access, and then the access is going to be automatically removed, by some batch job, right? And that is OK to me, because even though there may be a potential for sort of abuse, I've restricted the people that can do these sort of things. And I also always have run into that problem. If I gave an analyst access to a MySQL database through a MySQL console, they will always try to exfiltrate data. Inherently, giving the people data access opens you up to data exfiltration.
Yeah, I guess I'm worried that you can't really revoke access. So if you find out somebody was up to no good, they've got the keys now. You could re-encrypt the entire cluster, I guess, at that point. But it seems pretty heavy.
First of all, on top of this, there is other layers of security in that analysts only get access to the zones by the firewall. If they have a need, so we even revoke access to the zones that actually give you access to Hadoop. So we even revoke those things. And then we actually have this goal, this ambitious goal of rotating our certificates in our PKI very quickly. Maybe imagine that you rotate all the access credentials to Bletchley every day. So even though you captured somehow the access credentials a week ago, now you cannot use them anymore. So I think that the principle is sound, and you can build things on top of it to mitigate the risk. But at a very fundamental level, it's a problem that is unsolvable. In that if you give access to people, there's always a risk. So that's why you review the code changes that are committed, and for custom data access, you need to restrict the number of people that can do that.
Just one more quick question. Have you considered using something like Hadoop streaming to do the encryption outside of the process that's running the job? That seems like a good way to make it more difficult to get a hold of the keys. You could imagine decrypting the protobuf, giving the decrypted thing to the code that's running the user job. It might also save you from porting your library to every protobuf language.
So one of the nice things about porting our protobuf library is that we can use this across not just Hadoop, but also Kafka, sorry. So Kafka is we use this for our message bus. Internally, we call it SAMSA. So it's kind of nice to have this same message format across all of our apps. Our apps can speak to each other using these protos. They can use message buses, and it's the same thing in Hadoop, right? So it provides us really nice uniformity to the API, which is really nice. So it definitely helps putting it as part of the protocol at the protocol level. As far as using Hadoop streaming, It's an option, certainly. It requires a little more work when it comes to integrating with other analytical tools like Hive or with Presto or with any of these other tools that are out there, right? So it's about which part of this did we want to hook into, and we picked the part that was sort of the smallest.
Thank you.
Yeah.
Hi, I have a couple of questions. Do you want me to ask all at once or one?
Whatever you prefer.
Whatever you prefer.
So the first question
You can load
is,
balance if you want.
have you deployed this solution in production, and what has been your experience? So does it achieve what you expected?
So we're in the process of deploying this to production right now. So this is not complete by any means. I don't know if you mentioned that early on, but yeah, definitely haven't actually taken this to scale yet, to be completely direct. But we have pretty high hopes about it.
Got it. The second question is from developers' perspective. You mentioned some of the benefits of making it transparent to developers, but it also comes with some limitations, as you mentioned. Have you considered an alternative, which is that you can build a layer on top of product buffer as an alternative? What are the trade-offs? Can you elaborate on that?
What limitation do you see about making cryptography easy for developers, though? I mean, maybe I don't agree with one of the points is that I think that there is only upside about making crypto easy for developers. There is almost no downside.
Okay, so the downside I was referring to is that in one of your slides you mentioned that it's difficult to implement the same mechanism when the message can be nested, for example. Yeah. But if you build an API on top of product buffer, then product buffer doesn't have to be changed, right? So that can support this.
Yeah,
so, but every company is different. If you don't need that functionality, which is
there's actually a really great reason for it. I think Cedric's about to say it.
So one of the reasons is we wanted to work with third-party code.
Yeah.
So if we use external libraries, that write data in protocol buffs, we still want that stuff to be encrypted.
And that's one part of it. And the other part is we want to support field-level encryption. Sometimes you have heterogeneous messages, some with perfectly OK data that can be in the clear, like transaction amounts, for example. Or it might be something we might actually want to redact transaction amounts at some point, because there may be some of our partners that are sensitive to their gross payment volume, for example. So we could tag based on a merchant or based on the kind of specific fields that we care about, right? So it's useful to hook into the language definition itself, because then we can tweak, right, rather than separate the data. As soon as you separate the data, now you have to do these joins, which become fairly awkward for developers.
Yeah. We can talk more offline.
Absolutely.
That's a good answer. Thank you.
Yeah.
The last question is that you mentioned that you are caching the key, right, for a day. I can think of a vulnerability there, but it sounds, I would guess there's a trade-off somewhere, right? So now your key is cached somewhere. So have you given more thoughts about that?
So I guess Nathan and Diogo will talk about how we think about making every attack online. But when it comes to Hadoop, it's such a different thing that it's hard to think about it, because even if you do make all of your attacks online, right? And now you see, imagine that instead of caching or anything, we just did online decryption every time because we didn't care about performance. Now you're seeing a billion decryptions in 30 minutes. Is that an attack? Is that somebody trying to exfiltrate data out, or is this somebody just running like a big job? So it's hard to understand, right? So I think that we don't necessarily cache the keys for a day. We cache the keys for the lifetime of the job, and keys are encrypting data in time intervals. And there's going to be a negotiation between us and them, making this shorter and longer, maybe an hour.
maybe a month.
The data is cached for the lifetime of the job, and I guess that's kind of inescapable. The job itself will have access to the data for as long as it lives.
Okay, so because I'm not very familiar with Hadoop, so just to clarify, can different users or analysts share the same job or is it a limit? A job is mapped to a particular analyst, a particular user.
So an analyst, when they run a job or write a Hive query or something like that, would kick off a series of MapReduce jobs, and the analyst is running as themselves, right, on the cluster. So that's how that job has access to the things that analyst has access to.
If we run it as themselves, you can think that there is like the HDFS file system, there is an XT4 file system that actually holds the credentials to access the online decryption service, Bletchley, and those credentials have like Unix style permissions so that only analysts that are in certain groups or services that are in certain groups can access certain access credentials. So that's the actual.
Understood. So the cache to key cannot be shared among users.
It doesn't cross the job boundary, right?
Yeah. Okay. Good. Thank you.
Hi, I'm Srinath from Facebook Security. So I see two things here. One is like access control, and one is like encryption, keeping data not accessible to everybody, right? Do you guys have an option to turn off encryption and just enforce access control? For example, you might want to tag field saying who can access what, like mostly like an authorization problem, and just enforce it at the MapReduce job level, right? Whenever job comes in, it's going to say, go ahead, and then before retrieving the fields, it's going to look at, can this person access this? No encryption, nothing at all, but just enforcing. I feel like it could be more scalable, and you don't have to worry about the key management and everything. It could be just, I'm not just saying it's a replacement, but could be.
Yeah, no, I see what you're saying, actually, and it's definitely a lot simpler, right? Just to tag a field with who can access it. One of the problems, though, is that when it's at rest, which is actually stored in HDFS, when it's on disk, it's now unencrypted. And so there is definitely a physical attack there, right, where you can walk away with the drive. So that's certainly something that we've thought about, but that was one of the things we were optimizing for. Daniele, you want to add?
And in general, I think at that point you'd have to trust something on the box itself to enforce things on the box itself, and that tends to be hard. Right. But I guess, yeah.
Kernel patches across your Hadoop cluster take time.
Actually, no, because you have to have some sort of like.
Yo, we're on a Hadoop job to kernel patch, right?
Hi, my name is Mark Horowitz. I'm also here at Facebook. Can you talk a little bit more about your authorization model? You kind of glossed over it saying we already have one, but you just kind of have three roles. You kind of have sensitive and then personal and then nothing, or is there something more in depth than that?
I think we'd have to just understand, go through all the pieces of data we currently store, and understand what is the disjoint set of things that we can sort of mix in a way that makes sense, divide, so that at a high level it makes sense. Some of the people in the security team wanted to have per data type encryption keys, so that you'd have access to only name and email addresses and maybe, I don't know, geolocation, right? But I thought, I actually was pushing for the other thing about having classes of data, because in my mind, people tend to access similar categories of data. So the chances that you're accessing the email address, given the fact that you wanted to access name, is very high. So the conditional probability is high. So I think any sort of commonsensical division of these types of data is a good one.
And we can certainly expand on this later. If we wanted to start breaking up and add another tier, we can certainly do that and run a re-encryption job to actually update data if we needed to. So it certainly allows us the flexibility of adding more granularity, I think. At least that's what we believe, but we haven't done one of those yet. So.
Thank you.
I have also another answer for you. It's just that we really like crypto.
Hi. It's kind of a follow-up question. I see that your protobuf definition has those extensions. It won't be easier to try to put like more type hinting, like this is a credit card, and not this is personal or this is. So what kind of data you are storing that is a personal email? So rather than putting a string as data type, have you considered maybe going further and say this is a credit card, and credit card has a certain automatic groups and everything.
Yeah, that's actually a good point, but still putting that data types inside buckets, I could see that working. I mean, in your specific example, we're not going to store credit card data. I think we're going to force data eng to, if ever they have to access any of that data for any reason, maybe for compliance jobs, because they have to do anything that has to do with legal or compliance reasons, we will force them to do online calls on these types of data. So I don't see credit cards specifically, but it is generally like seems like a sound idea to type data by type and then being data automatically fall into buckets. That definitely sounds feasible.
One nice thing that we can do with types is that, let's say your type is a user. A user has many subfields, right? It could have a first name, a last name, an email address. But it also might have some sort of innocuous data, like their current gross payment volume, for example. So we want to be able to leave gross payment volume completely in the clear, maybe, because it's easier to just analyze that directly. But we don't want access to name or email address for other jobs. So it's the typing can be on actual entities rather than on specific fields. And if it's we're not going to do this for credit cards, but if we were, I would say credit card would be the type, and a subfield would be card number. And that's the only encrypted one, but we're not going to do that. Yeah.
Cool. I think we got to wrap up questions here. Great. Thanks a lot, guys. This was great.
Yeah.